So the answer of the question just now is actually convolutional neural network. So convolutional neural network is a go-to for image classification problems. And we can see later on, image classification problem is actually the base for object detection problem. So a refresher, convolutional operation. So in CNN, as the name suggests, we need to perform convolution. And this is a brief animation of how does convolution works. So, yep, this is the animation of how convolution works. And we can kind of see in the left, there are convolution and max pooling. So if you guys attend the previous workshop, which is convolutional neural network workshop, I believe that you guys probably know why convolution operation is important for image. First of all, convolution operation outputs is known as feature map. So what does it contains? It contains features such as edge, lines, corners, and everything that we want from the image. So that's the main idea of convolution. We want to extract the high-level features of image. By extracting them, we are able to get information such that we can classify a bunch of image. And later on, we're going to use some of the CNN architectures. Even though it's not mentioned here, we're going to use a quite powerful one. So we'll see that later on. And then for convolutional neural network, these are some of the building blocks that I've discussed in the previous workshop, convolutional neural network. So there are three main layers, which are convolution layers, pooling layers, and connected layers. So convolutional layers is where we do convolution. Pooling layers is when we want to downsample the feature maps or the of the layer. So we try to decrease the size of the data, but still get some of the feature from the data itself. And lastly is the connected layers, which is normal fully connected neural networks, which is all the neurons in the previous layer are connected to the next layer neurons. So with that in mind, let's go to object detection. So for object detection, we have many different architectures or many different models for solving object detection problem. There are RCNN, YOLO, ResNet, SSD, and much more. Yesterday, one of my colleagues discussed about RCNN. So if you guys haven't watched the workshop, you guys should watch later on when the recording is available. But for today's workshop, we're going to discuss more about what is actually object detection in terms of YOLO. So first, before we discuss about YOLO, we need to discuss what are the data set that YOLO use. Especially there are various type of YOLO. So first of all, we're going to discuss about version 1 YOLO. So version 1 YOLO use Pascal VOC. Pascal VOC dataset is quite popular, well known, and it consists of 20 different classes. And out of these 20 different classes, there are 11,530 training image and 27,450 annotated objects. So the main idea of this is that we have 20 classes. That's the important thing that we want to capture from this slide. So moving on, we have scoring for object detection. So when we want to, like, let's say we have a model, right? How can we know whether our model is actually performing well or not? Well, we need to see whether the object detected from the model is actually near to the bounding box. So what are these bounding box? So when we want to train a model, right, we always need to label the image ourselves. So there are some people out there that search for this image. They draw a bounding box for the specific objects, then they label the name. So that is called ground truth. And what we want to see is that whether our model can get an area similar to the one given from the model. So how can we measure the similarity? We use IOU, or intersection over union. So the idea is that we can see from here that the intersection is the area that is intersect by the ground truth and by our model prediction. So the idea is that the intersection is the one labeled in cyan color, and the union is the one with the purple color. So with these two area, when we divide, we should get an area, a number between 0 and 1. So that's the main idea, to get what is the scoring for the object detection. And here I mentioned that the correct bounding box, for example, is intersection over union greater than 0.5. And most of the time we try to have a threshold for object detection, and later on we will discuss this in terms of coding it. The next type of scoring for object detection is actually PR curve, or precision recall curve. So the idea is that it every time we run the object detection, there are several different class, and we want to see for each specific different class and the threshold, we want to see what are the precision and what are the recalls, and we try to balance both of them. So we try to balance both of them, right? So we try to use a method called area under the curve. So if we use area under the curve, then we make sure that when the precision is high, we can see that the recall is not as high as it is. But when the recall is high, the precision is not as high as it is, right? So we try to balance both of them using the area under the curve. So this area under the curve is called average precision. So it's called AP. And this is only done for single class. And then for our thresholding, for our type of scoring the object detection, we'll use mean AP, or mean average precision. So the mean here comes from the fact that there are several different classes. So we'll take the average in the sense. So there are different types of IOU. So IOU, as I mentioned earlier, there are some 50%, there are greater than 75%. So we'll try to see to combine the MAP as well as the IOU. So this is how we score object detection. Any questions so far? Okay, I think we can continue. So yesterday, we discussed about RCNN, or region with CNN features. So we don't want to discuss about this in details, but the idea is that out of these four, we can see that the last region, or the last steps that we need to do, is to actually classify the regions. And this is completely different from YOLO. As later we will discuss, YOLO is not a classifying problem. It's a regression problems. So that's the main difference between RCNN and YOLO. And in yesterday's workshop, we discussed a bit about selective search. And selective search is used to, we want to get the bounding box. So we try to get a fewer proposal where the bounding box is for RCNN. But for YOLO, we won't be using selective search. As for YOLO version 1 and RCNN without any modification, or vanilla version of RCNN and YOLO, we can see that YOLO have a lower MAP over RCNN. However, we can see that the speed is like maybe like 100 times different. So we can kind of see that it's actually much more faster when we are using, actually it's 1,000 times faster, I think, or sometimes faster. And we can see it's 45 FPS compared to 0.5 FPS. So that means 0.05 FPS. So that means every single second, YOLO can invert 45 different frames, while RCNN can only invert 0.05 different frames. So that's the main difference between YOLO and RCNN. And this is why YOLO is quite popular, because not only that the precision is not as high, but it's still usable for real-time application, as the speed is quite fast. Usually for object detection, we try to have FPS around 20 to 30 for autonomous vehicle. So we try to see which model can do that, and YOLO is one of the models that can do that. So moving on, let's discuss about YOLO version 1. So let's say we have an image. How can we do an object detection? So we can see there's a dog here, we can see there's a bicycle here, and we can see there's a car here. We can see 3 different objects in a single image. So how can we classify them one by one, as well as knowing where are the location of the object using bounding box? So first, YOLO approached this by dividing the image into S times S grid. So S times S grid means that, let's say the image is, let's say 400. If we divide it by 20, that means there will be 20 times 20 grid. So for this case, from the paper, is divided by 7 times 7 grid. And this is the implication from the paper of YOLO paper itself. So we try to divide it to S times S grid, but in our case, we try to use the one that is put on the paper, which is 7 times 7. Then, let's say for each grid, we try to see whether there's an object or not. So for this grid, we try to predict whether there's an object or not. Here we try to predict the probability of whether there's an object or not at that specific grid. So let's say for this one, I think there's a car. So the YOLO will try to predict this specific grid, and it will tell, oh, the probability of the object being in that specific grid is quite high. So it will do for all the grids here. Similarly, not only the grid of the probability of whether there's an object or not at that specific grid, it will try to predict whether there's a bounding box that can fit to that specific object. So what do I mean by that? It tries to get the property of the bounding box. So bounding box have 4 different properties, which is one of the point in the bounding box, or let's say the center of the bounding box, and the width and height. With 4 of those properties, we can actually get any different types of, we can use those 4 properties to draw any types of bounding box. So with the center point, X, width and height, we can get all the bounding box for any types of objects. So that are the 4 parameters that YOLO are going to predict. So it will do all the prediction for all this grid. So for this specific case, we only do 1 bounding box, but it can be 1 grid can predict more than 1 bounding box, as we will discuss later on. So if let's say we use 1 or 2 bounding box for each grid, we will have this lot of bounding box, and then these are not yet the final result, but we will combine this with the class probability. So what are class probability? Class probabilities are the probability whether that specific grid contains a specific class. So it does not like have a correlation with the object yet. It just try to see the probability whether at a specific grid, the probability of that specific grid being a car, a bicycle, dog, or dining table, or any sort of class that we have. So we try to separate the class of a specific grid and whether there's an object. So we try to split those two into different probabilities. which is called the cross probabilities, and the other one was the objectiveness or P object. Lastly, once we have all of this, we can combine it into one single thing. So we have these class probabilities corresponding to a specific bounding box, as we mentioned earlier. So once we combine this, we can get this one. So this one, this specific image is the combination of both the bounding box that is generated by all the grid plus the class probability corresponding to that specific grid. So remember that a specific grid can have several bounding box, but that specific grid at YOLO version 1 can only have one class probability. And we will see the implication later on. So we can see there are a lot of bounding box, but this is not what we want, right? We want to have only one bounding box for each image. So how can we do that? We can do threshold and maximum suppression. So there are several ways to do threshold and maximum suppression. I list one of the methods that is commonly used for object detection method, which is here. Later, you guys can read this on your own. But basically, the idea is that when you have the prediction, you have different types of scoring of confidence scores. And what is confidence score? We'll talk about it soon. It's about the probability of a class in the object. So that will be discussed sooner. And basically, the idea is that we have different types of scores at specific grid. So we try to see whether that specific grid have a high probability of that object. So we try to see the IOU or the intersection over union. And then after that, we check whether there are somewhat higher level. If there's not a higher level with that specific same class, then we just ignore it. If there is, then we take that one as a newer one. So that's how we do threshold and non-maximum suppression. And now we'll discuss about what are the outputs. So we mentioned earlier, right? We discussed that we divide the image into 7 by 7 grid. So the output of this convolutional neural network should produce 7 by 7 grid. And this is what we see. Not 7 by 7 grid, but 7 times 7 tensors, sorry. So this is what we see. We can see there are 7 and 7 tensor. And then what is the, I guess we can say, let's say this is the width and this is the height. Then what is the depth of the tensor, right? So the depth of the tensor we can see here is equals to 25. So remember that I mentioned for one bounding box, we only require 4 specific parameters that we need to discuss, which is the x, y, width, and height. And we also discussed that at that specific bounding box, we want to know whether there's an object or not, or probability of object is there or not, or objectiveness. So we have 5 different things that we can get for a bounding box. And then at that specific grid, we want to see what are the probability for each different types of image, right? So at that specific grid, we may have, like, let's say for our specific data set, we have 20 different classes. So we have 20 different probabilities. And that's the main idea of YOLO. YOLO is not classifying. YOLO is predicting. It's trying to predict what are the position of the bounding box, trying to predict what are the probability whether there's an object or not at that specific bounding box, and what is the class probability for each different classes at that specific grid. Notice that grid is not equals to bounding box. One grid can have several bounding box, and we'll discuss about like how many bounding box should we use for, let's say, one grid, and how can we make sure that our grid can have, like, get a better accuracy of that specific image. So let's say for this specific case, right, we only have one image, one bounding box for each grid, which is the the one we discussed earlier here. So that means for each image, we can see that there is only, for each bounding box, we can see there is only P object X, Y, width, and height. So this is one bounding box, right? And then we can see that if we try to have more than one bounding box at a specific grid, we can actually expand it. And we will discuss about this soon. But now let's see about how can we discuss with top-down approach. So just now we are trying from bottom up. So bottom up is where we already like try to have, we don't have the object detection yet, but we try from the image to object detection. So what about the top-down approach? So maybe some of you guys can better understand with top-down approach. So I'll try to explain it as well. So top-down approach method to discuss about YOLO is that, let's say this is the output of the YOLO network. We can see that the output is the bounding box here. And we can see that at that specific point is the center of the bounding box, which is one of the which is two of the parameters that the network predict, which is the XY, as well as the other two parameters, which is the width and height. But for now, we can focus on the center one, which is actually the center of the bounding box. So the center of the bounding box is actually at that specific point, which is corresponding to the grid in yellow. So at this specific grid, right, how can we know this is the last point that the network predicts? So actually, this is not the last point that the network predicts. Let's say our network is actually predicting two different bounding boxes. And the result is actually like this. We have two different bounding boxes for the same image. And we can see that the center for these two bounding boxes is not the same. And the reason why the one we saw earlier is actually located at the different bounding box is because we already apply threshold and non-maximum suppression. But the idea here is that we can see for one specific grid, we have two different bounding boxes if we specify it equals to 2. And for each grid, let's say for two bounding box, we have X, Y, W, and H. So we have a total of 5. Whether there's an object in the grid, the X, Y, W, and H parameters, but for that specific grid, only one class probability. So only one class probability, which is why this was examined as a person. So to sum up what I mentioned earlier, the idea is that when we have this specific image, we feed into our YOLO network, then our YOLO model will predict, will try to predict for all several cells, right? We have 1, 1 to SS, which is 7 times 7 for our case. So let's say for cell 1, 1, which is the one in the top left. In the top left, we need to predict two bounding box. That means we can see there are two different bounding box and their own confidence score, which is the probability whether there's an object or not at that specific bounding box, right? But for the cell probability, there's only one probability for that specific grid. So it's not actually corresponding to the bounding box, but it's actually corresponding to the grid for the class probability. But for the whether there's an object or not, is actually correspond to the probability of the bounding box. So it's kind of bit difficult to grasp at the first time because you have two different probabilities where one is corresponding to the grid one and the other one is corresponding to the bounding box. But it should be quite familiar with you soon as we're going to do a different version of YOLO. So before that, I have one question for you guys. So just now I mentioned about this type of thing quite a lot, right? So my question is that, let's say for a specific YOLO model, we want to have two bounding box for each grid. My question is, what is the result? Will the tensor be something like this, or will be something like this? So I'll send the poll, and maybe around 1 minute, you guys can try this one. So good luck. So this is the first one, and this is the second one. So let me check. 7. Okay, so this is the first slides. This one is the second slides. No need to see what is the dimension. I think I mistyped the dimension in the poll, but you guys can see this is the first one, which is 7,730. The second one is 7,725 plus 25, which is 50. So choose the one from the image. No need to see the one in the polling, because the one in the polling, I think I typed it wrongly. It should be 7,730 for the first slides and 7,750 for the second slides. So this is the first slides. This is the second slides. Okay, I think we can end the poll. So from the polling result, we have a tie for both answers. And I think it's because one of the confusion I made earlier, which is the 7,730 and the first slides. But anyway, I'll re-elaborate what I tried to say for this specific question. So the question asks you whether when you have two different bounding blocks correspond to a single grid, what will be the output tensor? Will it be 7 times 7 times 30 or 7 times 7 times 50? And the simple answer is that it will be a 7 times 7 times 30. And the reason is that for each bounding box, for each grid, there will be two sets of bounding box, but there is only one class probability. So the class probability will stay the same for that specific grid. And but the specific grid have two different bounding box, right? So the two different bounding box is corresponding to this one and this one. So I hope that will clear up some confusion just now. So remember that the YOLO network will divide the image to different grids, S times S, which is 7 times 7. And then for each grid, there will be one close probability, but there are several bounding boxes that will try to determine whether there's a probability of an object at that specific bounding box. So for this example, since we have 7 times 7 grid, but we have two different bounding boxes for each grid, so there will be two different sets of bounding box properties or parameters, but there's only one class probability corresponding to that specific grid. So just now we were mentioning about class confidence score. So we can touch about it here. So class confidence score is more about mathematics. So I try to put it on the back a bit. But the idea is that we have three different probabilities that we are trying to get for a specific grid. So let's say for a specific grid, right? We want to see whether there's an object or not. This is the probability of an object. Then for a bounding box, we want to see whether not only there's an object or not, but whether the location of the bounding box is correct. So how to do that? We multiply both of the number, which is the probability of an object times the IOU, or the intersection over union. So by that, we get the box confidence score, which is, are you sure there's an object there? And are you sure it's quite close to the one in the ground truth or the training data? So that's the first probability. Then the second one is conditional class probability. So I mentioned earlier that each grid will try to predict what is the probability of that specific grid being a cat or dog or a person. So that is this type of probability. It's being independent from the object. And the reason why is that we don't want to tie out a grid with a specific object. We try to tie out the grid with only the object class. So we don't want to have it to be too like combine both of the features at the same time, but we try to predict two several things. And once we know, because if we try to combine those at the first time, right, that means we don't have the sense of whether there's an object or not, and every number will be quite different. So it will be much more difficult to determine, to train the model. So that's why we split it into two different tasks. In such a way, when we know there's no object there, then we don't need to do the conditional class probability, because once there's no object there, we are quite sure that we don't need to continue for that specific grid, because for that specific bounding box, because there's no object there. And the class confidence score is the combination of the conditional class probability and the box confidence score. So that's how YOLO version 1 works. And for the network architecture of YOLO version 1, as I mentioned earlier, we have the output of 7 times 7 times 30. So this is actually being implemented in the paper. So in the paper, this is based on the GoogleNet architecture. And in the paper, it is being used as there are 20 different classes. Note that the 20 different classes is because of the data set of Pascal VOC being 20 different classes. Then we have 2 times 5. So remember that for each bounding box, we have 5 parameters that we can get, which are the XY, WH, and the probability whether there's an object or not at that specific bounding box. Since we have 2 different bounding boxes, we have 2 times 5. So we have 10 plus 20, which is 7, 7, 30. So we can see the output is being 7, 7, 30. And you can see from the network style, we can kind of replicate the network model like 7, 7, 64 and everything of the convolutional and max pool. But the idea is that this specific network are being trained for like several weeks. So their model, their weights are already being optimized for a specific data sets. So that's why, even though we can, let's say we want to recreate this using Keras or TensorFlow, we won't be able to like get a great performance directly. As what they did was they have several different types of data sets to feed in for the object detection. Whereas we don't have this kind of amount a huge amount of data sets and a huge amount of GPU's power. So that's the main idea. Whether we can use this, we can, but we still need to train it with different types of data set, with different types of GPUs. So that's the main idea of this object detection. We try to use someone else that have trained this, and we can try to fit it for our different data sets. So if you guys see earlier that there's a problem with this YOLO version 1, right? So we can see for this specific image on the right, we can see there are 1, 2, 3, 4, 5, 6, 7, and 8. So, but the one that is detected on the left is only 1, 2, 3, 4, 5. And this is the reason why YOLO V1 have some problem with the accuracy. It is because each grid is already tied for one object. Even though you have two different bounding blocks, it's only one specific object. So that's one of the main problem of YOLO version 1, where if you divide it by 7 by 7, that means by maximum, you can only have 49 different 49 different objects. So that's one of the main problem of YOLO version 1. And we see later on how can we tackle this in such a way that for each specific grid, it can be tied to multiple different objects. So this is where YOLO version 2 comes in. So YOLO version 2 is called better, faster, stronger. So there are a lot of improvement from YOLO version 1, and I'm not going to discuss all of them, but what I'm going to discuss is the three main factors that shows the difference between YOLO version 1 and YOLO version 2. So there are several different factors, but the one that we are trying to focus on is the anchor boxes, dimension cluster, and direct location prediction. So first of all is the anchor boxes. So remember just now we were only using 2 for YOLO version 1. But here we're using 5 for YOLO version 2. And we can see that for YOLO version 1, we don't have any specific like criteria for the bounding blocks. We let the network predict, okay, you want to be W equals to something, H equal to something. We let the model do it for us. We don't care about that. But here, YOLO version 2 takes it differently. Instead of predicting what is the bounding box, we give them anchors or priors. And the reason why it is called priors is because from this specific priors or this specific bounding box, you can just add an offset or you can minus some offset from that specific bounding box to fit an image. So these 5 different anchors, they are already being fit into the model by using k-mean clustering. So k-mean clustering, for those who haven't touched about this subject, is a way to get, it's not a classification or regression problem, but it's a clustering problem where you try to see how does the data sets plays out in the image. So for our case, our image, there are several different types of image, right? We try to see what are the bounding blocks that can fit, and we're using IOU for this case. So remember that we have 5 different bounding blocks, and these bounding blocks are called priors. And from these priors, we add a certain offset or minus a certain offset from these priors. And how can we determine the size of the priors is by using k-mean clustering. And actually, this is what it is called dimension cluster. So dimension cluster is, in the paper, they apply this k-mean clustering to all this image, which is the Pascal VOC data sets. They apply it one by one, and they can kind of see which of them fits the whole data sets the best, which 5 of them. And the reason why it's 5 is because when they do the clustering, they compare it with the average IOU, which is one of the scores for the bounding box. And what they get is that they can always increase the number of cluster or the number of bounding box. But what they are trying to get is actually, if you increase the amount of cluster or the amount of bounding box, that means you need more higher computation, and sometimes you want to trade off between performance and the computational complexity, because the main idea of this YOLO is not about only performance, but it's about speed as well. So if you want to trade off, you need to make sure that your model is not only fast, but it can predict quite well. And that's the main idea of YOLO version 2. So that's why the cluster is 5. It's chosen by the author itself. And lastly, we have bounding box encoding. So I mentioned earlier, in YOLO version 2, we actually predict not the bounding box itself, but we predict the offset from the bounding box. So how does it look like in the mathematical terms? So we can see from here, in a mathematical terms, they actually have several different things. So B is actually the bounding box property. So we can see Bx, Bw, By, and Bh. These four are not the things that we predict. The things we predict are labeled with T. So we see here Tx, Ty, Tw, and Th. So the idea is that we applied some function that correspond to some we apply some function to the prediction, let's say Tx and Ty, to be around this specific box. And usually the function, since we already linearized the box, let's say from here is 0, this is 1, this is 0, this is 1, so this is 1, 1. So we already use a certain function, let's say like sigmoid activation function, to the probability in such a way whether your number prediction is from negative to infinity to positive infinity, you will get a bounding box from this specific location. And that's the idea of Bx and By. And Cx and Cy is the offset from the top left of the image. So this is not the thing that we are trying to predict, but this is already given from us. But for Bw and Bh, we don't want to predict the offset using linear terms. We want it to use exponential terms. As I mentioned earlier, if you use exponential terms, then you can fit in a number from negative infinity to a positive infinity, and you still get a number between, let's say, the b equals to 0 to b equals to some number of multiply of p. So that's the idea of the offset. So the offset is actually Pw plus some number, but in this case, the offset is actually multiplication of it. So we can kind of simulate the offset being the Pw of ETW minus Pw, but it's still an exponential difference. So with this term, we can see that the performance from the paper of YOLO, with the change of this, that we don't predict directly the x, y, w, and h, but we instead predict this t, x, tw, ty, and th, we get a better performance. So we also try to improve the quality of the object detection, right? So what we have earlier, the problem from YOLO version 1 is that at a specific grid, we can only have one image assigned to that grid. So for, let's say, 7 times 7, you can only have 7 times 7 object assigned to a specific image. And to tackle this problem, the idea is that for each bounding box, you can have a specific class probability. So that's the main difference. So last time, for one grid, they only have one class probability consists of the 20 class. For this YOLO version 2, one specific bounding box have 25 different predictions. So for 5 different bounding box, we have 125 different prediction. So for this one, we have the x, y, w, and h as usual to describe the bounding box. We have the probability of the object being there in the bounding box. And we have a probability of the bounding box object. So whether it's the class of the bounding box, so whether it's a cat, it's a dog, or anything, it will be corresponding to the one in the bounding box and not to the one in the grid. So with that, you can actually, for one grid in this scenario, one grid can correspond to 5 different objects. And we mentioned earlier that to have a small object detection, we have a medium object detection. We already preset the anchor point to be 5 of this thing. So that means the YOLO object detection, not only that it can detect an object, 5 different objects at a specific grid, but it can also detect a small object, medium object, or large object at that specific grid, which is one of the main problem with YOLO version 1. So this is the network architecture for YOLO version 2. And we can see that this is taken from Darknet 19. So YOLO is always taking a network from someone else. Like for example, YOLO version 1, it takes from the Google Net, and YOLO version 2, it takes from the Darknet 19, and it edits some of the, it modifies some of the network. And we can see here, the Darknet 19 consists of 19 different convolutional layers. So if we add 1 plus 1 plus 3 plus 3 plus 5 plus 5, we get 18, which is why it's called, even though it's called Darknet 19, right? We exempted one of the convolution layers, which is the one that is used for image classification. And instead, we modified it into adding 3 convolutional layers here and concatenate with the 5 convolutional thing here. So it's a completely, not completely different network, but it is based from the Darknet 19. So the question here is that, what is the output for Pascal dataset that have 20 different classes, 5 anchor or 5 preset bounding box for a 7x7 grid? So the poll starts. Question 2. All right, launch poll. Okay, so I've launched the poll. Okay, I think we can stop the poll now. So from what I see here, there are another tie answer. So 7 times 7 times 125 and 25. And the correct one is actually 7 times 7 times 125. So 25 is only for one single anchor point. So if we have 5 different anchor points, then we have 125. Because now for each grid, we have 5 different bounding box, and for each bounding box, we try to predict 25, and we can see it here, where we have 25 different prediction for one specific anchor point or specific bounding box. So here we have 5 different bounding box for one cell. So that means we have 125 different predictions for each grid. So that means 7 times 7 grid times 125 predictions. So I hope it clears the confusion. And before we go to YOLO version 3, I would like to ask you guys if you guys have any doubts regarding to the YOLO version 1 and version 2. You guys can either type in the chat or just unmute yourself and ask the question. Okay, I think we can continue to YOLO version 3. So we have discussed YOLO version 1 and YOLO version 2, and the problem with YOLO version 1 have been tackled by YOLO version 2, right? Such as whether the YOLO version 1 is unable to detect a lot of objects in the same grid cell because the object is maybe too small to be detected, or there are a bunch of objects at a specific grid cell such that the grid cell is unable to make the decision for all the different objects, which is actually countered by YOLO version 2. So what will be the next version of YOLO version 2? I mean, it's YOLO version 3, but what will be the improvement for it? So we can see that there are 2 main improvements for YOLO version 2 to YOLO version 3. And the title of the paper is called an incremental improvement. So there are 2 things that YOLO version 3 takes it differently from YOLO version 2 or version 1, which is doing the class prediction and doing the feature pyramid network. So first of all, let me remind you about the class prediction. So just now, when we were discussing about all the probability of the class given the object, each of the grid cell for the YOLO version 1 or each of the bounding box for YOLO version 2, the probability must add up to 1, which makes sense because the probability is using the softmax function, and there cannot be like one objects have 2 different class. But for YOLO version 3, we are going to have these problems because we are using a different types of data sets. So remember that for version 1 and version 2, they are using Pascal VOC, and for the version 2, they are also using ImageNet, but they are always in a same kind of that data sets, or in a same in the class. They don't have clashing, like two different class can have one of the same meaning in the object. But for YOLO version 3, they try to tackle this problem, even though the problem is not really quite severe. So the idea is that, let's say for a given image, let's say in pedestrian, right? A pedestrian can be classified as a pedestrian and as a person or as a child. So that means there are 2 different classes assigned into a same object. So how can YOLO solve this problem? Instead of using softmax function, they are just going to use a normal sigmoid and binary cross entropy loss. So it will be 1 versus all instead of all of the class being divided using softmax. So that's one of the improvement for the YOLO version 3. So not only that it is able to detect the one object, it is able to detect actually several different class prediction. So that's why there are, I think for YOLO version 3, for one object, they can have 3 different class prediction. So that's one of the main feature of YOLO version 3. And then the other one is feature pyramidal network or feature pyramid network or FPN. So FPN is being used for YOLO version 3. And one of the main reason is that, remember in YOLO version 2, we did the bounding box, we did the anchor, and we kind of already assigned what is the small one, what is the medium one. We have 5 different bounding box. But for this case, instead of like we divided for 5 different bounding box to tackle all these problems for the small, medium, and large, in this case, they are using 9 different bounding box to tackle each one for a different size of image. So we can see here at layer 82, they do the stride equals to 32. So what is the stride? So stride is actually, if you guys remember from the previous workshop, stride is actually dividing the input size of the image by the number of stride plus 1. So the idea is downsampling the image or downsampling the layers. So we can see when we do downsampling, we can see that the image become quite small. Then with the stride of 32, then we have a stride of 16, and lastly we also have a stride of 8. So with these 3 different strides, we have 3 different image size, which is small, medium, and large. And for these 3 different image size, we have 3 different anchor or 3 different priors, right? Or the bounding box that we try to modify. So all of these are predetermined. And for Coco dataset, which is the one that is being used to train the YOLO version 3, they are using this specific width and height. So you can see for a small one is 10 times 13, 16 times 30, and 30 times 23. This is for the small object. Then for a medium one or this one, they are using 30 times 61, 62 times 45, and 59 times 119. And for the big one or this one, they are going to use these 3 different values. So they have anchor for different shape. So remember in YOLO version 2, we only have 5 anchor to tackle all the problems. Here they divide it into 3 different problems. They divide it into the small one. So for the small one, they are going to use this bounding box. For the medium one, they are using these 3 different bounding box. And for the bigger one, they are using these 3 different bounding box. And that's the main difference between YOLO version 2 and version 3. That's why it's an incremental improvement. So with all those in mind, let's discuss about how can we train all this YOLO version. We need a loss function. And YOLO loss function, we can simply divide them into 3 different loss: confidence loss, localization loss, as well as classification loss. So for let's discuss one by one. So for the confidence loss, right? The idea is that confidence loss is when if an object is detected in the box, then the confidence loss is used. We will use binary cross entropy to solve this, right? So that's confidence. So confidence is when if there's an object detected, then you try to measure the confidence loss. So if there's no object, right, then the confidence loss won't be even incurred for that specific bounding box. Then the second one is localization. So what is localization? So localization loss is that it's a loss that is measured when there's an error, which is the predicted boundary box and the sizes. So we try to see whether there's an error for the sizes and the bounding box. So for the, remember for the confidence is about whether there's an object or not. For the localization, whether the size is similar to the one that is in the training or not. And lastly, we have the classification. So classification, as we mentioned earlier, we are using two different types of loss, because if we're using softmax, then we're using multi-class cross entropy. If we're using sigmoid, we're going to use one versus all binary cross entropy. So it depends on YOLO version. So for YOLO version 1 and YOLO version 2, this will be the three things that they are going to use for the loss. And for YOLO version 3, they are going to use the binary cross entropy loss. And remember that all these three loss have different weights, and depending on the paper, they use different types of weights for the loss. So this weights is trying to tell the model to fix this certain problem. So if you put more weights on the confidence, then the model will try to fix the confidence problem. And even though we know that it's trying to fix it, in the neural network, we cannot see where is the specific layer that is doing this, because it's a neural network. So that's one of the problem of neural networks in general. But for our case, we don't need to go dive into all these three different equation for the loss function. We just need to know that to optimize a certain parameters of the loss of the one that we want to try to increase the performance in the neural network or the YOLO model, we can just have a higher weights at that specific problem, so that the model will try to reduce the loss. Especially, let's say if we have higher weights in confidence, then the model will try to fix the confidence problem. And of course, we have tried several things. Like in a couple of years, there have been a lot of models, not only YOLO, but there are SSD, RCNN, RetinaNet, and everything. So we can see that mass RCNN on Coco is around 41 MAP. So mass RCNN is the one that is done in the previous workshop. So for our workshop is labeled with, the legend is using pink star. So we can kind of see it's here. So it's actually before the graph. So it's actually good, because we want to have lower inference time. So we can see here the inference time for YOLO version 3 with the input image of 320 times 320, the inference time is only 20 milliseconds, which is very fast. And you can see mass RCNN is not even detected in this graph, and it's around somewhere around here, I think. So it's around 300 to 400 milliseconds. So that's one of the main, I guess, the main advantage of YOLO, because you see that even though the accuracy or the average precision for YOLO is not as high as the other, which is like, let's say RCNN is quite high, like 60 or something, it is already quite enough to do, let's say, to compare it with SSD, which is one of the model that is quite popular as well for doing object detection in your phone or in a small computer. So we can see YOLO is actually having a lower inference time, but still having a higher average precision, which is the ideal case. So with those in mind, we can finally go for the coding session. So for the coding session, I will share this link on the chat now. And I think it will take maybe around 30 minutes to finish the code. So we can now have around 5 minutes break before we go for the coding session. So during these 5 minutes, you can ask me any question or any doubts you want. Okay. So just now there's one question. So one of the question that the participant asked is that what is the function of YOLO loss function? And as any models related to neural network, we try to optimize the weights, or in this case, the filters of the convolutional neural network, right? So we do need to have a loss function in such a way that it will backward propagate to the backward propagate the CNN to update all the filter weights. So remember that we are using this CNN network, and we try to optimize all the filters that is used to do the convolution. So that's the main idea of the loss function, is trying to update all the parameters or all the weights in the CNN, which is this specific convolutional neural network. Okay, so let me check. Can you guys see the new screen for the YOLO workshop.zip? So I'm going to show you guys how to import this to Google Colab. So first of all, you guys need a Google account, which I assume all of you have. And then to get this to our Google Drive, we need to use zip extractor. So with open zip extractor, it will automatically extract all the zip file inside. So this is the zip for the code and for the all the stuff inside. So first, we'll just need to wait. So you guys can kind of follow this step because I think it may take some time for the zip to be extracted. Okay, so we can see here there are some content of the zip. What we need to extract is all from collab notebooks to the one in the IPYNB. But unfortunately, if we untick this, it will untick all of the one that we want. So we just tick everything. So it should be fine for us. And just click the extract button. So just click the extract button directly. So the extracting will take times, especially for the two here, YOLO v3 weights and model.h5. So YOLO v3.weights, you can technically download it from the source, but I tried it just now from the Google Colab. It may take some times. So I think extracting it would be much more faster in our case. So I'm not sure whether downloading it is much more faster or extracting it, but I think from my experience, extracting it will have less amount of time. So you guys can try to extract this and put it on your folder soon. All right, the extraction is complete for mine. So once the extraction is complete, you just need to press the view files. So what you need to do, since we only want to get the folder for the collab notebooks, just need to go a bit down to the collab notebooks. So we found here is the collab notebooks. So we have the YOLO workshop. So we can drag it here, put it on the My Drive. So it has been moved to the My Drive. So after it is moved, right, you can kind of see the YOLO workshop here. You move it to the collab notebooks. Since I already have mine, so there are two different folders, but for you should have been only one folder. So for my case, I can just choose one of these as I've done this before. But for you guys, there should only be one folder. So remember to put it under the collab notebooks and YOLO workshop. And the YOLO workshop is actually from the one that is from the extraction one. So once we have moved here, there are three different files and two folders. So this one is just the checkpoints and we don't need to really care much about it. We just need to see there are the IPYNB and two different weights. So these two different weights, they take quite a while to download. So that's why the extraction take a bit long. And actually from these two weights, only one of it is important, which is the model.h5. But to show for this kind of purposes, which is to get it directly from the creator, I'm just going to show both of this and how it is being implemented. So since I'm not sure whether you guys have already extract this or not, I think I'm just going to give you guys some time. Maybe we can start around 8:35 for the IPYNB if you guys are okay. So let me know if there is any problem with the extraction. I don't think there is any, but if there is, just let us know in the comment section. think we can continue. Does anyone have a problem on opening the IPYNB file? So as I mentioned earlier, we get the model file, which is the YOLO feat3.weights from this source. And there are two different methods of doing it. And the first one is to ignore this one. There are two different methods of doing getting the model from the website. So the first one is actually mounting my drive. Since my drive already consists of my drive contains the model.weights, right? So we don't need to actually download it from external source again. Reload. Yeah. Okay. We don't need to actually download from the external source. Rather, we can just directly get from our drive. So that's the first method, which is much more faster. And the second method is just directly download from the source directly to our Google Colab. And you can see from here, it takes around 17 minutes plus 5 minutes. So it's around 22 minutes, which is not quite well for me. So that's why I anticipate this and try to use the Google Drive approach by extracting instead. So if we run the first code, and assuming that you guys put the Colab notebooks on the right location, this one should be running correctly. So this line of code is just to mount your Google Drive and get all the weights, all the custom image and everything. So you need to open this link. Then you choose your Google account corresponding to that Google Colab. So for mine is this one. Then once you click allow, you will have, I think, a given some random gibberish word that you need to copy. So you just copy, close this one, then paste it, then press enter. So by right, it should be mounting. And you can see you should get 4 of this thing, which is the custom image folder, model.h5, YOLO.ipynb, YOLO.weights, YOLO feat3.weights. So out of these 3 different files, excluding the YOLO feat3, the custom image is the folder where we can try to play out later on if we do have some times. The YOLO feat3.weights is the one we downloaded from widget, but we don't need to do that since we have already downloaded for you guys in the first place. And the model.h5 is the one that we are actually going to use for the workshop. But I'm going to show you guys how do I obtain this YOLO feat3 weights converted to model.h5. So a bit of backstory. If you go to this specific link, you can see that it's actually made by Darknet, or the one that is creating the YOLO version 3 itself. And it's actually created using C. So since they are using C and we are trying to use Python, we need to convert it in a way that from a floating point numbers into the one that we can understand, or at least our model can understand. And since we are using 106 layers, I tried to use TensorFlow beforehand, but I think it would be a bit more difficult to do that. So what I did is that I see that actually there are someone else have been doing this to convert the model from YOLO version 3 in the C++ into Python. So this code is based on that specific person. So the idea is that we want to convert all the value from the weights into something that we can use for a model. So these are all the things that we can just run. So you can see here there are all this specification. Actually, it corresponds to the one I was mentioning earlier in the presentation slides. So if you guys see in the presentation slides here, and then we can return for a bit of slides. There are in the slides 82, 94, not slides, layer 82, 94, and 106. These three are the layers where we did the downsampling and did the striding, right? So if we see here, layer 82, and then layer, what is it, 94, and layer 106 is the thing where we apply the striding and stuff. And we actually did implement it inside here, but you can see the stride, we just put it equals to 1. The reason why for this kind of scenario where the stride is not equals to the 1 in the neural network design is because they already implemented for the weights inside there, so that we don't need to change all this. And this is actually being discussed in the GitHub. So if you guys want to know more about how do we implement all of this, we can directly check the GitHub for this case. Yep. But aside from that, if we run this code right directly, if we run this code, it will actually produce model.h5. So since we already have the model.h5, we don't actually need to run this code. But if you guys want to run it, it's up to you guys. For me, since it should only take a while, if we run here, it will actually replace the model.h5 located on our drive. So if we click here, we can see that our drive, if we go to the collab notebooks YOLO workshop, then we can see this model.h5 will be replaced. And we can see it's currently loading the weights of convolution 80. So there are 106 layers, so it needs to load one by one all the weights. And I think should be finished, right? Okay, then the other thing that we can do is to download an image for our COCO dataset test. And I've done this for you guys, so it's up to you if you want to do this. For me, I have done it, and you can kind of see it in the custom image / COCO test. There's one image available. So this is the thing about the coding time. So just now it was only for model conversion. Now we are trying to actually program the entire thing. So I didn't put any exercise for this YOLO workshop because it's a bit difficult for me to place the exercise itself. But I was planning to explain all of this for you guys. So the one on the top is only conversion, and I don't think it's really important for you guys to really understand, as some people already actually have the model.h5, so we can actually use the model.h5 directly. So now I think we can discuss more to the how we implement the H5 model to detect the object detection. So first of all, what we need to do is that we have some image, right? And this image is from internet, and usually it's in RGB space. They have the range of the pixel value is from 0 to 255. So what we need to do is we need to convert it from 0 to 255 to 0 to 1, which is explained here. And then our neural network, if you remember earlier, is actually a size of 416 times 416. So if we see here, it should be 416 times 416. I'm not sure whether it's correctly labeled, but it's actually around that specific size. in the paper. So we're just going to use 416 and 416. And then that's the main idea for image. So we need to pre-process it by, first of all, change the shape into 416 and 416, make the range from 0 to 1 instead of 0 to 255. So that's what I did here. And remember that the data type of the image should be classified as float 32 or 4 bytes of float for the data size for the floating point. Instead of using double, we're just going to use float 32. And this is usual for implementing it in class. So the second thing that we need to do for the object detection is the bounding box. And bounding box is one of the important or the essential part of object detection. Because without bounding box, even though we kind of know where is the location from the network output, we need to translate the network output into the image, right? So I did several functions, and the important part from the bounding box is that we need to show the bounding box. We need to show the information of the bounding box, such as not only that you can draw the X, Y, W, and H, but at that specific bounding box, we need to know what are the class and what are the whether there's an object or not, and whether there's a class and what are the class at that specific object, right? At that specific bounding box. So those are the things that we need to consider. So remember, we want to know the objectness, we want to know the classness, which is implemented here. And we have, instead of using the X, Y, W, and H, and we're going to use matplotlib to implement the drawing, it's better to use xmin, ymin, xmax, and ymax. So later on in the code, you will see that I convert some of it from the X, Y, W, H to this form, which is easier for us to draw it later on. So here, the get label is only to get the class label for the specific bounding box. So this one not really important for now, but the idea is that we have label and score, right? So we try to get the data from that specific label and get the score of the specific classes. So that's the idea of the implementation of the class here. And remember just now I mentioned about we try to change the box to xmin, ymin, xmax, ymax, or something like that. It's actually implemented here. So remember that we want to have it in terms of xmin, xmax, ymin, and ymax, so that it's easier for us to draw the bounding box. This is implemented here. And this one is just some other function. And the bounding box IOU, this is how we actually measure the IOU. So IOU is basically, we just need to measure the area, right? And if we have the xmin, xmax, and ymin, ymax, it will be easier to determine the W and the H for both. Then for the area of the intersection, we use the internal overlap, which is what I implemented here. So this is how you get the IOU of the, which is between 0 to 1. And then for the boxes, right? We want to append it to show the box later on. So this is only to show whether there's a bounding box above a certain threshold that we put. And remember that I put 0.5 in the example for the slides. Here we're going to use 0.6, but you can always change it later on for the code. And then we have also draw boxes, right? Draw boxes, the idea is that we try to draw the box of the rectangular thing. So even though I only implement v boxes, v labels, v scores, which is the location of the box, the label of the box, and the score prediction of the box class, we can also have a color change. So we can actually change the color later if you guys want to try out with different colors for the box. And this is just some sigmoid implementation. And the main, I can say the main thing about the toolbox that we are required for this interpretation of YOLO is the decode net out. So if we check here, the third thing that we require is to interpret the output of the network. So remember that the YOLO output, the model output is in some kind of form that we may not be able to use directly without converting it into some other types. So that's the function that we're going to do, which is decode net out. So decode net out is basically getting the output of the network and changing it into a certain things that we want, which is the bounding box. So the idea is that we want to convert the output of the model into a bounding box. So this is implemented here. And remember that we implement for the anchor, we have 4 different formulas, right? Which is the offset cx plus some function sigmoid or something, which is implemented here. So we actually implement the exponential function here. And the reason why we divide by some grid, right, is because we try to normalize it between 0 and 1. So to normalize it, we just use division with the, let's say for the xy, we just divide it by the grid size. And for the width and height, we just divide it by the total width of the image and the height of the image. So this is how we can get I guess we can get the bounding box. And then one of the other things that we mentioned is that we always want the object to be at higher than certain threshold to draw the image. If it's not higher than a certain threshold, then we will just ignore the image, right? And it's actually implemented here. And even the output of this will have some, I guess, some collision between many types of bounding box. So we still need to use non-maximum suppression. So remember that non-maximum suppression, the idea is that if there are more boxes there are a lot of collision box that determines the same type of class, we try to actually reduce the number of class. And the implementation here is actually the one I use in the slides. So the 3 steps that I put in the slides, the pseudocode, and I implement it in Python. So this will actually reduce the number of bounding box into the one that we want. So with all those in mind, this is actually only the toolbox. And if you guys have used Keras beforehand, I think you guys know how easy it is when you have a model.h5 and you want to get the model output, right? You just need to do model.predict after it is being trained, which is already been trained by the YOLO by using Cocoa dataset for several weeks or months. Then we already quite sure that this weight is quite, like the weight is quite, I guess, optimized for almost all the data sets that contains these certain labels. And if you guys count this or just use labels, length of the labels, you guys can see that it should be 80, which is the amount of Cocoa dataset classes they have, which is 80. So here, remember that we put the class threshold equal to 0.6, then the non-maximum suppression is equal to 0.5. So once you do the prediction, you decode the output of the prediction into boxes. After you have the boxes, you try to implement the bounding box and apply a non-maximum suppression. Once you do that, you should be able to draw the box. So if we run this one, we should get an output of showing that there's a certain type of object in a certain bounding box. So if we run here, YOLO is actually quite fast, but the reason why it's not fast as you guys think here is because there are some pre-processing, and the model inference time is actually only this specific region here, which is to predict. That's all. but the image processing afterwards is not actually implemented in the model.inference. So when they say about FPS, is actually this amount of time taken here. 1/that amount of time is the FPS. And we can see here, there are several objects being detected from the model. So there are, these are the model outputs directly without having, let's say these are the model output directly implemented after we apply the functions such as the non-maximum suppression, getting the correct boxes and everything. And we can see here, we try to print out all the labels and scores, right? And the labels are persons, the scores are quite high, around 99%. And I think there's some accuracy with 88%. So we can kind of see that for this specific model, they already fit it, optimize it for almost all the COCO data set. And this is where you guys can kind of play along. So if you guys have been listening to until this point, but you guys haven't run all the code, simply you guys can just delete some of the code I mentioned earlier, like only like for example, you don't need to run some of this, like this one, the second method, and the first one you don't need to run it, and the rest you can just press the runtime, then run all below, I think. Yep, run after everything. So by right, you should be able to run everything until the last one, and you guys can play out with this. So let's say you guys want to use another image and you want to implement it directly. So let's say we can search for another image here. So let's say COCO image example or some image, right? You can search for any image. Let's say you just need to wait and search for any image you guys want and then implement it. So this is one of the example that I use. So this is quite interesting that it's able to detect everything. But let's say you guys have your own image that you guys want to implement. So let's say, I'm not sure, image example, object, dataset. I'm not sure. So let me search image example COCO dataset or something. So the idea is that we kind of want to get the image, then we try to implement an object detection on it. So let me check which one I can try. So this one I have tried, but I am not sure whether I can find another one. Oh, I can find this one. So what we need to do is just right click this, copy the link address. Then what we can do is we just scroll about a bit here. We paste the link to this one, right? Then we just put COCO test, let's say 2. So what it does is actually it's downloading the image and put it on our custom image says COCO test 2. So if you guys check the Google Drive, there will be additional image. Then what we need to do is just change this one to COCO test 2, then run it. Let me see, cannot identify the image. COCO test 2. Okay, let's see. Okay, let's see. Okay, I think we need to see whether the data is correct or not, because sometimes it's not actually showing the right thing. And you guys can actually just upload some image directly. So we can see here the Cocoa test 2 is not working. So I think should be correct if I press the copy image address. Let me try it again. Okay. So it's PNG, right? So we just need to change this to PNG. Run the same thing. So by right, we should see there's a new Cocoa test2.png. Once it finished download the stuff, then after that we can directly run the last line of code. So far, do you guys have any other question since we change this to PNG, and then we should be able to run and see the results. So remember that only object being labeled from here can be detected, and luckily there are ships I think somewhere here, so it is able to detect the ship as well as the person. So we can see that the object detection works quite well, and I think there is one object being detected as dog, and I think there's a small dog somewhere there. I'm not sure, but you guys can try it out with all your custom data set, and you should be able to run this. So I think that's the end of the workshop. If you guys have any problem with the code, you guys can let me know now. And while we're at it, we can, let me change the slides. So if you guys enjoy this workshop, please do some feedback for us so that we can actually improve the quality of the workshop. Thank you so much.